This video is one in a series that explains how to use the program Comprehensive Meta-Analysis. This example works with proportions. This is one of a series of videos. I'm assuming that you've already seen the video how to enter data, and in this video we're going to be looking at how to run a basic analysis. The data set that I'm using here is discussed in our book Introduction to Meta-Analysis. In the prior video I showed you how to enter the data. The first study is SAINT. There are 65 patients in the treated group and 65 patients in the control group. 12 events in the treated group, 16 events in the control group. The program computes the odds ratio and the log odds ratio and its standard error. To run an analysis, we simply come up here and we click on the button that's marked Run Analysis. And the program immediately shows me for each study the odds ratio, the lower and upper limit, the z-value, the p-value. That information is shown over here as well in the form of a forest plot. So for the first study, for example, the odds ratio is 0.69 with a confidence interval of 0.30 to 1.6 approximately. Here is the null value, which is 1.0, and the point estimate is 0.69. And the confidence interval goes from 0.30 to 1.6. As is always the case, if the confidence interval includes the null, the p-value is going to be greater than 0.05. In this study over here, the confidence interval includes the null, and therefore the p-value is 0.39. For this study down here, the confidence interval does not include the null, and the p-value is less than 0.001. Down here we have the overall estimate of the effect. We're currently looking at the fixed effect model. The overall estimate is 0.49 as an odds ratio, with a confidence interval of 0.65 to, with a confidence interval of about 0.35 to 0.65. We see that over here. This does not include the null. The p-value is less than 0.001. We can also switch to a random effects model by simply coming down here and clicking on the word random. When we do that, the effect size shifts. Under the fixed effect model, it had been 0.49. Now it moves to 0.59. So it moves a little bit closer to 1, and the confidence interval also becomes a little bit wider. It might be easier to see that if we look at both of them at the same time. So I'm going to come down here and click on both models. We can see that under the fixed effect model, this is the point estimate. Under the random effects model, it moves to here. Under the the fixed effect model, this is the confidence interval. Under the random effects model, it moves to here. It might be instructive. The choice between a fixed effect model and a random effects model should always be made based on what is conceptually reasonable, and rather than looking at this sort of after the fact. However, it's sometimes instructive to see how the different models assign weights differently and how that impacts on the effect size estimates. I can come up here and click on this, which is Show Weights, and then what we see, for example, is that this study over here, a study called Lane, is given under the fixed effect model. It's given 40% of the weight. Under the random effects model, it's given only about 25% of the weight. And this, just by coincidence, happens to be a study that had the largest effect. Since we're dealing with odds ratios, as you get further and further from 1, the effect gets larger and larger. And so what happens is, under the fixed effect model, where this is given 40% of the weight, it pulls the effect way to the left, which is why the effect size over here is 0.49. By contrast, under the random effects model, it gets a proportionately less of the weight, only 25% rather than 40%. Therefore, it has less of a pull on the overall effect size, and the overall effect size is closer to the consensus of the other studies, and it's 0.56 rather than 0.48. So that's sometimes a useful way of looking at the weights and trying to understand what happened. I'm simply going to switch to the random effects model right now, because in this example I'm going to assume that is the more appropriate model. And when I do that, the fixed effect model goes away. I have my random effect weights. I have the overall estimate of the effect 0.56, lower and upper limits of 0.35 and 0.90, z-value of 2.37, and a p-value of around 0.02. There are many other things that we can do. That's the basic analysis, but there are many other things that we can do in the analysis screen. One thing is that over here we're looking at the odds ratio. I also have the option of looking at the risk ratio. The numbers are going to be somewhat similar. In this example, the risk ratio, the overall estimate is 0.64. We see again the effect size and confidence interval for each of the studies. I can also shift to the risk difference. And of course the scale changes now. We're looking at risk differences. In this range, the overall effect is an estimate of minus 0.11, meaning that the mean risk in the treated group drops by about 11 points compared to the control group. You can also see, by the way, that when we are working with risk differences, the amount of weight assigned to this study is substantially larger than the amount of weight that had been assigned to this study when we were looking at risk ratios or odds ratios. That is not necessarily going to be a general rule, but it does apply in this particular case, and it helps if you're trying to figure out why you're getting a different effect in one metric as opposed to another one, to be able to see how the weights are shifted as you move from one to the next. In any event, I'm going to move back to the odds ratio, which is the example that we used in the book. I can click up here on Next Table, and the first thing we see is at the top we have the line for fixed effect model, and below that we have the line for the random effects model. In each case we have 6 studies. The point estimate is 0.49 to 0.56. We have the lower and upper limit, the z-value, the p-value. Everything over here relates to the test of the null. In the case of the fixed effect model, it's looking at what we assume is the common effect across all of the studies and asking if that is significantly different from the null from 1. In the case of the random effect, we're looking at the mean effect across all the studies and asking if that's significantly different from 1. In both cases, the p-value here is less than 0.001. Here it's around 0.02. That's everything over here. On the right-hand side, we're looking at the heterogeneity. We're looking at the dispersion among the studies, and we're saying we see a certain amount of dispersion over here. These studies appear to be lined up more or less in a row. This one is somewhat out to the left. The amount of dispersion that we're seeing, can that be all due to sampling error, or do we need to reject that hypothesis and say that at least some of the dispersion that we're seeing is due to real differences among the studies? To put that a little bit differently, even if all of the studies shared a common effect size, we would not expect them to all have exactly the same effect size in the observed data, because there's going to be random sampling error within each study. But what if each of these studies actually had an infinite number of patients in it, so that the effect size that we see for this study represents the true effect size for that particular population and that particular variant of the intervention, and so on for all of the other ones? In that case, would we expect all of these to line up in all having the same value? Or in that case, would we expect to still see some dispersion from study to study? That's the question that we're asking when we ask about the heterogeneity. And in this case, we're saying that the test of heterogeneity is given by a Q statistic and degrees of freedom and a p-value. The p-value is 0.06, which means that it is possible that all of the dispersion that we're seeing here really is just due to sampling error among the studies, and that if we actually knew the effect size for each study exactly, it's possible those would all turn out to be the same. But the p-value does approach 0.05, which is the conventional level for a test of significance. We're saying that if in fact all of the studies really shared a true common effect, then the likelihood, then the chances that we would see this amount of dispersion would only happen about 6 times in 100. So, I mean, therefore, there's a decent chance that at least some of the dispersion that we're seeing is really true dispersion in effect sizes. The I-squared is 52, and what that means is that the amount of dispersion that we're looking at over here is the observed dispersion. But we know that at least some of that is just due to random error. If we could somehow go back and remove the random error so that what we were looking at was only true dispersion in effect sizes, what would that dispersion look like? And what we're saying is that the I-square is 52, which means that if we removed the random dispersion and just looked at the true dispersion, there would still be some dispersion, but not as much as we see here. And the dispersion would be reduced somewhat, that about 52% of the dispersion that we are seeing is real. So, which means that about half of it is error. So the variance of this dispersion, if we think of variance as how much these vary from each other or from the common estimate, that would be reduced by about half. And just to be clear, we're talking about the variance over here. So it doesn't mean that the dispersion that we're seeing, if we think about this as a standard deviation, we're not saying that the standard deviation would be reduced by half, but we're saying that the variance would be reduced by about half. To put that another way, we can compute the variance for each of these, working with each of these points over here. That gives us the observed variance, or we could remove, using a formula that I'll mention in a minute, the part of the variance that we assume is error, and then we'd be left with the dispersion that reflects the true variance. So the ratio of the proportion of the true variance, the variance that we get based on the true effect sizes, as a ratio of the variance that we're seeing over here, that would be about half. That's what the I-square of 52 means. Tau square, if we come back again, we could compute the standard deviation of these effect sizes, how much they vary one from the next, and we can compute the variance of these effect sizes. But again, that's not a terribly informative number, because that variance represents the variance in the observed effect sizes, and what we really care about is the variance in the true effect sizes. The fact that tau square is 0.17 and tau is 0.46 tells us that if we went back and brought this and removed some of this dispersion, so that what we were left with was only the true dispersion in effect sizes, that the standard deviation of that dispersion would be 0.46, and the variance of that dispersion would be 0.17. Now, how do we actually compute that? The formulas are explained in a great amount of detail in the book, but the basic idea is that we're able to look at this and say, if all of these really shared a true effect size, and all of the dispersion that we're seeing is just due to pure sampling error, then there's a certain amount of dispersion that we would expect. And how much that is depends on how precise each of the estimates is. If all of these studies were very large, we would expect to see relatively little dispersion, since it's all based on sampling error. If many of these studies are small, we would expect to see more dispersion. But you can compute how much dispersion you would expect to see. We compute that, then we take a look at how much dispersion we actually are seeing, and the excess, the amount of observed dispersion relative to expected dispersion, gives us an estimate of how much dispersion there is in the true effect sizes, how much the true effects vary one from the next. And critically, the number that we take out of here is tau square, the variance of the true effects, because that's going to be something that we use in assigning weights to the studies. Let me come back here for a minute and point out that all of these statistics relating to dispersion, the Q value, the I-square, the tau square, the tau, are all presented on the line for the fixed effect model. A question that I am often asked is, what about computing these statistics for the random effects model? And this is really just a source of confusion. The answer is that these statistics are always computed using fixed effect weights, but they are then applied to the random effects model. And because the statistics are based on the weights over here, but the statistics are then applied to this model, there's a certain amount of natural confusion. In some computer programs, I think, list these statistics on the random effects line because that's where they are used. We list them over here because that's where they are computed, but it really doesn't make a difference. The numbers are always computed based on the fixed effect weights, and they are always applied to the random effects model. And what I mean by that is that under the fixed effect model, we are making the assertion that the true effect for all of the studies is identical. Once you make that assertion, in effect what you're saying is that tau squared is 0. There is no true variation in effect size, and that I squared is 0. The proportion of variance that reflects true differences among the studies is 0. And therefore these numbers really have no applicability to the fixed effect model. They do, however, matter when we move on to the random effects model, because over there we are using them to describe how much of the variance is real, and what is the how much of the observed variance is real, and what is the quantity of variance of the true effects. I should also note, by the way, that the p-value, in a sense, does apply to both models. It tells us, it addresses the viability of the null hypothesis. Under the fixed effect model, we are asserting that all of these studies share a common effect. If the p-value is less than 0.05, then we're saying that that is really not a viable hypothesis, that it is unlikely, based on the empirical data, that the studies share a common effect because there's too much dispersion. The amount of dispersion that we're seeing is not consistent with that hypothesis. If I come back over here, there are various other things that we can do. At the moment, I'm working with the random effects model, so let's continue with that. At the moment, the yellow line down here shows us the combined effect, and each line, the line for each study, shows us the effect and confidence interval for that particular study. If I click on the line that says one study removed, we're going to get something very different. What we get now over here is the effect size and confidence interval, not for this study, but it's really what we would see in the yellow line if we removed this study. In other words, it's the overall estimate of the effect and confidence interval based on every study except for this one. And this is the overall estimate of the confidence interval and point estimate for every study except for this one. So what we're saying is that basically if we were going to remove this study, what we would see is very similar to what we're seeing now. Based on all 6 studies, we have an odds ratio of 0.56. If we removed this study and redid the analysis, we'd end up with an odds ratio of 0.55. So really things have not shifted almost at all. And that holds true for all of the studies except for this one. If we were going to remove the Lane study, the odds ratio would jump from 0.56 to 0.79. It would become much closer to 1. And in fact, it would not even be statistically significant anymore. So this is telling us that this study over here has a major impact on the overall effect. And just to sort of show this in a little bit more detail, we can switch the scale over here, and let's say, so you can see that by removing, this is the null hypothesis again over here, you can see that by removing that study, the whole sort of conclusion is likely to shift. So we know that that is a fairly influential study in this analysis. Just to show you how this works, let me actually go back and remove that study and see what happens. The assertion that I'm making is that, the assertion that I'm making is that if we were going to remove this study, we'd end up with an odds ratio of 0.72. Let me come back to the basic statistics over here, and you see the odds ratio is now 0.56. I'm going to right click over here. I'm going to remove the Lane study, click OK, and sure enough the overall odds ratio now moves to 0.72 with an upper and lower limit of 0.49 and 1.0 and a p-value of 0.11. Let me go back and put that study back in. Something else that we can do, Now that I have all my studies back, if I go back to basic statistics, I have this. I can do a cumulative analysis. And what we're doing now is, let's assume for the sake of argument that these studies were entered into the database, and that we put the year that each study was done, and we sorted by year. What we're looking at over here is the cumulative amount of information that we have based on the first study, based on the first two, based on the first three, and so on. So that had we done a meta-analysis after the first 4 studies, this is the conclusion that we would have reached. After the first 6 studies, this is the conclusion that we would have reached. And of course, this one is going to be identical to this, because this is also based on all 6 studies. We don't need this. This is a useful procedure, not only if we want to sort this chronologically and see how the weight of the evidence shifted over time. It might also be helpful in other cases. For example, let's assume that we wanted to sort these studies from beginning with the large studies, which we assume are more reliable, and then adding smaller and smaller studies as we proceed. We can see if the effect size shifts once we begin to enter those smaller studies. If it does not, then that tells us that the impact of the smaller studies on the overall effect really was not very large. On the other hand, if you have a situation where the large studies show a very large effect, and then as we add more and more smaller studies, the effect begins to move in one direction or the other, that tells us that the effect that we're seeing in the smaller studies it tends to be different than the effect that we saw in larger studies. And it also shows us the magnitude of the drift and the substantive impact of the drift. So that can be an important thing to do in some cases. I'm going to come back to the basic statistics. We also have a tab over here marked calculations, and what that does is it actually opens a window into the calculations that were being done and lets us see exactly how all of these numbers were computed. If you are using the book, you will see that the numbers over here match the numbers that are given in the book for the calculations, and this is a useful way to understand exactly what calculations are taking place. I'm going to come back to the basic statistics. I showed you before that rather than working with the odds ratio, we can shift into the risk ratio or the risk difference. We can also look at the log odds ratio. Now, this is probably not going to be terribly helpful if what you are trying to do is to get a sense of the data, but it's very helpful if you're trying to understand the computations behind it. When we're working with ratios in a meta-analysis, we do not directly combine the ratios. So for example, if I come back over here to odds ratio, what we do not do is to take a weighted average of the odds ratios. Rather, what we do is we convert each of these odds ratios into its log value. We combine the log values, and then we convert it back to an odds ratio. So if you want to see how the calculations are actually being done, you can look over here at the log odds ratio. It is these numbers that are being used to compute the overall effect size. You'll notice also that when we switch to the log odds ratio, the program now shows the log odds ratio and also the standard error and the variance. You do not see the standard error and the variance when you're working with odds ratios, because the standard error and variance are in log units, and therefore to present them when we're dealing with odds ratios in raw units would be misleading and confusing. But when we switch to the log odds ratio, we do see them. Once we're looking at log odds ratios, if you then click on calculations, you can actually see the log odds ratio for each study. For example, for the same study, the log odds ratio is 0.366. And if you come back to data entry, you will see that it is minus 0.366. The variance for that study was 0.185. And if we come back over here and look at the calculations, you will see that the variance is 0.185. And if we switch to the random effects model by clicking on the bottom, you see that tau square is 0.173. And just to give you a quick run through then of how the calculations are done, this is the point estimate for each study in log units, the variance, the tau square. So we have here the within study variance, we have the between study variance. If we add those together, 0.185 and 0.173, we get the total variance. And then the weight that is assigned to that study is going to be 1 over the total variance. So 0.185 plus 0.173 gives us 0.358 1 over 0.358 gives us 2.793, and that is a weight that is assigned to this study. If we come back to basic statistics, we look at the weights, and we say show the raw weight, that is 2.79. That's the weight that's being assigned to the first study in this analysis. Coming back to calculations, and in a similar way we assign a weight to each of the studies. Then for each study we take the weight times the point estimate. So for the first study we have 2.79 times minus 0.366. So we end up with a column of weights and a column of the t-value times the weight. At the end of this, we sum these and we sum these. The sum of the weights is 17.5, so the variance is going to be 1 over 17.5. The sum of the weight times the point estimate is minus 9.9. The point estimate, in other words, the overall odds ratio in log units is going to be minus 9.9 divided by 17. If we take minus 9.9 divided by 17, we get minus 0.56, which is the overall estimate of the effect size in log units. And if we take the sum of the weights, that's 17, 1 over 17, is going to give us the variance in log units, and that is going to be 0.057. So that's how the computations are done. If we click on odds ratio rather than log odds ratio, what happens is the program, having done all of the analyses using log units, simply converts this back into an odds ratio rather than a log odds ratio, and then takes the lower and upper limit and converts those back into odds ratios, and that's what we see over here. The odds ratio is 0.568, and the lower and upper limit of 0.35 and 0.90. The z-value and the p-value don't change. Those are not going to be converted. Those had been computed using log odds values, minus 2.37 and 0.018, and those simply stay the same when we move back to the odds ratio. For those of you who were not able to follow that, that's perfectly okay. The program is doing all of the analyses for you. This was simply a digression to show you how those analyses are done. Something else that you can do over here is you can click on this little button, which is show residuals, and this is basically taking each effect size and comparing it to the overall effect size. The basic idea is that it allows you to quickly spot any effects which are very different from the overall effect given the amount of dispersion that we have here and here. In this case, none of them reach what we often see as a conventional threshold of 1.96, but even if they did, I want to be very clear, that does not suggest that the study is wrong. It simply says that it's an outlier, and you might want to take a close look at it and see if there's some reason why that study was an outlier and comment on that. It does not generally mean that you should simply remove it from the analysis. It might be a perfectly valid study, especially when you're working with a random effects analysis, and the studies are allowed to vary one from the next. They're being pulled from a presumably a population of different effect sizes, and if you happen to get one that is different from the others, it doesn't mean that there's something wrong about that. It simply means that it's different. At the same time, this is a good way of highlighting studies where you might have made a mistake in the data entry. You always want to go back and take a look at that. Okay, some other things we can do over here. Let me get rid of this for a minute. There's a button over here that lets you show the sample size for each group, and in fact I can right click on that and say show the total, so that for the treated group, for example, for this study, we're looking at 12 out of 65 events. For the control group, we're looking at 16 over 65. I can get rid of that. We have this tutorial that I can open up and that will walk you through most of the steps that I've been showing you over here. This is a good way to refamiliarize yourself with the program if you haven't used it for a while. If you show both models, I'm not sure if I did this earlier or not, but let me take a minute you can see that as you move from the fixed effect model to the random effects model, one of the key things that happens is that the studies which were very large, it's always going to be the case that the large studies get more weight than the small studies. That happens under the fixed effect model, it happens under the random effects model. But what changes is that under the fixed effect model, the large studies get a lot more weight than the small studies, whereas under the random effects model, the weights are more moderated. So that, for example, if we take the largest study, which is this study over here, and the smallest study, under the fixed effect model, this is getting 40% of the weight, this is getting 8% of the weight, so this is getting about 5 times as much weight in computing this number over here. By contrast, under the random effects model, this study is getting about 25% of the weight, and this is getting about 12% of the weight, so it's getting about twice as much weight in computing this. So the weights are more moderated. Just looking at the random effects model for a minute, what I find it's useful to do is to think about the relative weights and the raw weights. So if we show the raw weights, the raw weight represents the total amount of information that is carried by each study, whereas the relative weight represents the relative amount of information, obviously. So the raw weights really are what determine how wide the confidence interval is over here. Let me bring back the fixed effect weights as well for a minute. And in fact, let me show them both simultaneously. If you look at the raw weights, you can see that under the random effects model, the raw weights are always smaller. The raw weight for the first study goes from 5 under fixed effect to about 3. Under random effects, this goes from 3 to 2. This goes from 17 to 3. Under the fixed effect model, we have more information in the sense that we have a more precise estimate because there's only one source of error. The only source of error we're dealing with is a within-study error. And because we have a lot of raw weight, if we simply add these up, we're going to have a more precise estimate of the effect. Of course, all of this assumes that there is only one source of error, and that's why we have more precise estimates. Whether or not it's fair to make that assumption, it depends on how the studies were collected. But if it is valid to make that assumption, that's what's happening. Whereas under the random effect weights, we have less precise estimates, we have less information about the true effect, and therefore the confidence intervals are wider. So the raw weights determine the width of the confidence interval. By contrast, the relative weights tell us how much weight each of these studies is being given relative to the other ones. And under the fixed effect model, this study is getting a lot of weight, so it's able to pull the overall effect to the left in this particular example. Under the random effects model, this study is being given less relative weight. It has less of an impact. This study is not having as much of an impact on the overall effect, and therefore the overall effect is going to fall further to the right, more in line with the other studies. So that's a useful way, I think, of thinking about this. So one other thing is you can come over here and customize this set of information. You just right-click on that, customize the basic statistics. Let's say, for the sake of argument, I'm not a big fan of p-values, but let's say that you want to know the p-value for these studies, and you want to show more than 3 decimal places. I can come down here to p-value and say that I want to show 6 decimal places for the p-value, and then I know that the p-value for this study is, well, it's 0 to at least 6 decimal places. I wonder if we can pull it out further than that. Yeah, we can show 9 decimal places. And so that we see the p-value for this is, well, whatever that number is. It's, I think, a 4 in the 9th decimal place, and we see the p-value for this to more decimal places as well. Again, I want to emphasize, I'm just sort of showing off the program. I'm not a big fan of p-values myself. Let's bring this back to auto so that it shows the same number of p-values as everything else. And we also have the option, let's say, of maybe we really don't want to have the lower and upper limit and the z-value because that information is really captured in any event by the forest plot. So I'm going to remove the check marks next to these, and we'll show just the odds ratio and the p-value. Notice, by the way, that even if we check standard error and variance, those numbers are not going to be displayed when we're dealing with the odds ratio, but they will be displayed when we're dealing with the log odds ratio if they're checked. So in other words, the program is doing what it is supposed to do. You can check variance and standard error, but that only has an impact on the screen when it makes sense for it to have an impact on the screen. Let me show you also, I showed you before that you can display the odds ratio or the log odds ratio. You also, if you're working with the odds ratio, you can also display the Mantel-Hansel odds ratio or the Peto odds ratio, and then you can actually see the weights that are assigned under those. So let's say we go back to the fixed effect analysis. Under the inverse variance method, this study is getting 40% of the weight. Under Mantel-Hansel, it's getting 55% of the weight, so it's going to have more impact. And under the Peto odds ratio, it's going to have 47% of the weight. In some cases, as you move from one of these weighting methods to another one, the effect size might shift, and this helps you to understand why that is happening. I generally prefer working with the inverse variance, and that's what we get when we simply click odds ratio. And I'm going to get rid of the raw weights over here. They're useful for this kind of a didactic approach, but I think for purposes of just displaying this, simply working with the relative weights probably is more useful. I'm going to come back to the random effect weights over here. And I think that pretty much covers it. In future videos, I'm going to show advanced versions of this that show you, for example, how to bring moderators into this table, how to do a subgroup analysis where you compute the mean effect or the common effect for one group of studies versus another, how to do things like meta-regression, publication bias, and so on. Those are on other videos, and I invite you to have a look at those as well. Thank you for sticking with me.